The transition from silicon to silicon carbide is essential for high-voltage grid infrastructure. However, scaling production from 150mm to 200mm wafers has introduced severe crystallographic defects. In 2024, defect density on 200mm substrates averaged 3,700 defects per square centimeter. This is more than 4 times the density of mature 150mm lines. These defects, primarily threading screw dislocations, compromise the physical structure of the wafer. During high aspect ratio reactive ion etching, these dislocations concentrate electric fields. This causes localized gate oxide breakdown at voltages up to 30% below rated capacity. Consequently, manufacturing yields for 200mm trench devices remain suppressed at 58%. This is far below the 80% threshold required for stable, low-cost commercial volume production. The physical limitations of crystal growth are directly restricting the supply of advanced power electronics. Upstream semiconductor yield failures have triggered severe downstream macroeconomic delays. In 2024, the global supply deficit for grid-scale inverters widened to 33 gigawatts. Global demand reached 115 gigawatts, while actual shipments were capped at 82 gigawatts due to component shortages. This supply gap has caused procurement lead times to escalate dramatically. Average lead times for utility-scale inverters quadrupled from 16 weeks in 2020 to 60 weeks in 2024. This bottleneck has delayed over 30 gigawatts of planned solar and energy storage projects globally. The shortage is most acute in high-voltage classes, specifically 1,500-volt direct current and 3,300-volt alternating current systems. These systems rely exclusively on high-voltage trench silicon carbide devices to meet modern grid efficiency mandates. Without these components, utility-scale decarbonization projects cannot be commissioned. The transition to trench silicon carbide architectures represents a major electrical performance leap offset by manufacturing complexity. Trench devices achieve a specific on-resistance of 3.2 milliohms square centimeter. This is a 62% reduction compared to planar silicon carbide and a 97% reduction compared to legacy silicon. This architecture enables a highly compact die size of 25 square millimeters. This physical compaction theoretically increases the gross number of dies per wafer by 68% over planar designs. Furthermore, trench devices reduce switching losses by 92.8% compared to silicon-insulated gate bipolar transistors. However, these physical advantages are offset by a low 55% manufacturing yield at the 3,300-volt rating. This low yield inflates unit costs and limits widespread market adoption. Until crystallographic defect rates are resolved, legacy silicon and planar technologies will remain dominant in cost-sensitive grid applications.